everyone, and welcome to today's webinar on alternative water treatments for cooling towers. We have a lot to cover, so we're going to get started. And before we get started, I'm going to go over a few webinar logistics. Today's webinar is based on 3 reports by the National Renewable Energy Laboratory, and the 4 reports, as well as 1-page infographics and 4-page summary findings of GPG. And with that, I'd like to introduce Jay Fine. He's a project manager with the Center for Emerging Building Technologies, and he will be facilitating today's webinar.
All right, thanks, Andrea. I want to also welcome everybody to the call today. I would consider myself, I'm going to facilitate, but I consider myself kind of the bookends for this presentation. You're going to hear from me at the very beginning. I'm going to go through the agenda, and then I'm going to jump back on at the end, and I'll do the Q&A. In between, you're going to hear a really interesting presentation. Today, they're going to talk about 4 different technologies that are in a category that we call alternative water treatments. So, Andrea, can you go to the next slide, please? All right, so here's the agenda for today. So first, you're going to hear a quick introduction from Kevin Powell, who's the GSA Director for the Center for Emerging Building Technologies. After Kevin, we're going to have one of the technologies will be presented. It's one that came from GSA's Region 4, which is in the southeast corner of the United States. That'll be presented by Greg Tomberlin, who's with the Department of Energy's National Renewable Energy Laboratory. And following Greg, we're going to have what we call on-the-ground feedback. On-the-ground feedback is we want you to understand GSA's perspective on installation, operations, maintenance of that technology. And that'll be presented to you by Todd Kronline, who's with GSA out of Region 4. Following Todd's presentation, you're going to hear about 3 additional alternative water treatments. Those were conducted in Region 8, which is Colorado. And those will be presented by Jesse Dean, who's also with National Renewable Energy Laboratory. And we'll follow up Jesse's with the same type of on-the-ground feedback that will come from Tyler Cooper, who's within GSA's Region 8. Then I'll jump back on, and I'll do a couple of alternative water treatment takeaways for you, and then we're going to jump into Q&A. So I want to also reiterate before I move on and turn this over to Kevin, we're trying to mute everyone. We would appreciate if you just take a moment and mute yourself. There's going to be a lot of people on this call, and we're getting a lot of feedback. We have a new audio system that's a little bit challenging for us to get everybody to mute it if you didn't join at the onset of the meeting. So take a second to do that. And if you have questions, we encourage you to type those into that chat box that you see at the bottom right-hand corner of your screen. We're capturing those throughout the presentation, and then we'll circle back and I'll cover those at the very end. Okay, so with that, I'd like to introduce Kevin Powell.
Hello there, thank you. And so first of all, I want to thank everybody for joining this webinar today. This is one of, I think, it's a technology that we're going to talk about that has considerable interest in every region. And is probably one of the real defining kinds of reasons we have I'm okay, I think. Anyway, the whole point here is, oh, and I don't advance the slides. Who advances the slides? I do. Can you advance to the next slide? Right. So, key thing that I think that you'll hear today is that we have an incredible opportunity. More than 1/4 of all of the water that we use in our buildings goes to heating and cooling systems, and most of that actually to the cooling system, and in particular to the cooling tower. There's been a substantial increase in water rates over the past 3 years. And in fact, we project that trend to continue. So obviously saving water is a great thing. The challenge there's a whole host of technologies, and they have existed for some time around ways that you can reduce the amount of chemicals that you'll hear about how conventional water treatment is done. These technologies all reduce the chemicals that are used associated with traditional approaches, and they reduce the amount of water that you need to blow down to sort of maintain water chemistry. Now, I think as everybody knows, there's of these many systems out there, there's been a variety of experiences, and many of them have not been positive. So that's why we have a program like this to vet out which actually do work, and to make them work, what do you need in terms of O&M and in terms of changed practices. Next slide. There's 3 reports that we have recently published on this topic, and we encourage you to review them after this call. We're going to be coming up with a document that's going to actually look across all 4 of those reports and synthesize the outcomes. So let's see. With that said, I'm going to turn this over.
Yeah, my name is Greg Tomberlin, just as an introduction, and I work with the National Renewable Energy Laboratory. And as Kevin mentioned, we were in charge of doing the measurement and verification and testing out these technologies at the site. Next slide, please. These technologies, as Kevin mentioned, it's important. These technologies mostly save water. We actually look at water savings, chemical savings, and energy savings from these technologies and cases. The reason is, 25 to 50% of the cooling water is wasted in blowdown in these cooling water systems, depending on water quality and cycles of concentration and that kind of thing. Just as a rule of thumb, 1,000 BTUs to evaporate a pound of water, that's about almost 2 gallons of water for every ton-hour of cooling at a site. So the water issue is getting more and more important. Again, as Kevin mentioned, that the prices for water have gone up substantially around the country, so these technologies are making more economic sense as that happens. Next slide, please. The cycles of concentration, basically it's a ratio of solids in blowdown to make up water, or make up water flow to blowdown water flow. There's just a graph here that shows the economic benefits at different cycles of concentration. Typical cycles of concentration at a lot of these plants run between 2 and 5, 2.5 to 7. Normally we're going to see in the area of 3 or 4 cycles of concentration. And again, just as a rule of thumb, the cycles of concentration of 3, 33% of the cooling tower water then is being wasted as blowdown. But also, as cycles of concentration go between 3 and roughly 10, that's where the bulk of the savings are. If, after 10 cycles of concentration, the paybacks diminish at that point. Next slide. So just to go over this framework of how we tested the technologies, it was fairly similar in most of these reports, but I just want to go over that really briefly. We pick a site that makes sense and they're nice enough to host the technology there. We go out to the site and we decide, depending on what savings we're trying to measure, whether it's water, chemicals, energy. We decide what our target metrics are, what it is we're trying to achieve. We put instrumentation on the system, flow meters, temperature meters, CTs to measure energy from chillers and cooling towers and that kind of thing, depending on what we're trying to find out. We measure the makeup water coming in. We measure energy in some cases. In this case, we measured energy. We look at O&M, what was the cost of operations and maintenance of the system prior to the technology and post-technology. We measure blowdown systems, waste. We estimate drift losses of the cooling towers. And we do this over a period of time as a baseline where we study, the basic system and get a baseline for how much water is being used based on energy usage or cooling load. Then we install the equipment and we take data for another period of months to compare. And we use some of the typical M&V points on the right, including, load, outdoor air temperature, cooling tower status, water flow rates, and temperature flow rates, so we can compare apples and apples. Next slide. So we installed this at the Juliet Gordon Low building in Savannah, Georgia. They have two 150-ton cooling towers at the site. As you can see on the left, this is the technology that we assess, the dynamic water technology, which is an electrolysis technology. As you can see, it's a small skid. In this case, it's got 4 basically electrolysis canisters that sit right next to the cooling tower on the roof, and they actually take a slip stream of water. They don't treat the whole entire circulating water system. They just basically tap in to the cooling water line as it discharges from the cooling tower and then discharges after the system back into the cooling tower. Next slide. This is just a small graphic that shows what I was discussing. That reactor skid, in essence, is taking a very small slipstream, so it's not a really large skid in comparison. It does have a small pump on the system that pulls the slipstream water through the reactors. The energy usage for the skid is low. It's a 110 basically type spa pump kind of thing that plugs in, it could plug into an outlet. Again, it sits right next to the cooling tower, and there is a tap required into the piping of the discharge of the cooling tower, but then it discharges directly back into the cooling tower. This electrolysis process removes solids from the system to prevent scaling or to reduce scaling, which reduces blowdown and creates water savings. It also, during this process, creates chlorine, which is a natural biocide. So between the fact that it's reducing scale problems and introducing a biocide at the same time, water savings are seen, chemical savings are seen as well, and when we did the testing, we actually removed all chemical additives and turned those systems off completely. Again, the other thing we looked at was energy usage. We looked at pre and post energy usage for cooling towers and condensers as well. Next slide. Basically, the results of the testing was that we saw a 32% water savings from the system, and that was a result of basically a 99.8% reduction in blowdown. So in essence, when this system started up, we changed conductivity settings and that kind of thing to try to increase cycles of concentrations, but what happened for very long periods of time, the blowdown system really just turned off, and the solids and the scale and that kind of thing were being pulled out of the system by the electrolysis system. And again, we had 100% chemical savings, and what we did was turn off all of the chemical scale inhibitors and that kind of thing. But then when we assessed the system, we did before and after examinations and pictures and that kind of thing, make sure by removing those chemical savings or those chemical additions that we didn't do any damage to the system. Next slide. We also looked at the operations and maintenance costs. What we saw was roughly a 50% reduction in the O&M costs that were required, and a lot of that had to do with tower cleanings. Normally at the site, they performed 4 tower cleanings where they had to spend a couple of guys and several man-hours to spray wash, cooling tower fill, and reduce scale and that kind of thing. The site was very involved in this, the maintenance people, and their estimation was that the cooling tower after the system was installed was cleaner. I think the scale was easier to remove, and they felt that the number of cleanings could drop from 4 to 2, so we included those O&M cost savings. The site normally had used about $4,000 per year in chemicals, and those were removed. We did add in a maintenance contract for the system that was $6,000 a year. That was just kind of a standard contract. That can vary depending on the location of the site and how far travel time is and that kind of thing. But also, if the site personnel are willing to do more of this type of cleaning of the system, that price can be reduced as well. And you can see the pictures on the right. We were at the site when we pulled the system. You basically pull this centerpiece out of the middle of the tube, and you can see all the scale buildup, all the material that was removed. And the cleaning of the system that we witnessed, honestly, was fairly straightforward. You could take a knife to this stuff, and it came right off of these systems. I think somebody might need to mute their phone if they can, please. Okay, next slide. Okay, I want to go over the economics of the systems. Basically, we saw a 9-year payback, and that's looking at the cost of, lost my screen. That's looking at the cost of water at the site was $6.64 per 1,000 gallon. I think there's a lot of sites where that price is higher, and again, those prices seem to be going up every year. The installed equipment cost was right about $30,000 all in for the equipment and the installation. The water savings that they saw at the site were over 1.1 million gallons of water per year estimated. So that's a savings at that cost of about $7,500 per year. We put in the savings in the maintenance also from fewer cooling tower cleanings. When you add all the numbers together, we saw a payback of about 8.7 years, which is a simple number. We also calculate a savings to investment ratio of 1.7, but I probably won't get into that. So yeah, 9-year payback is the results of the system, and there are some variances in some of these costs. The installation costs, depending on the site location, the difficulty of installation, and the contracting entity, and some of those issues as well. So, okay, next slide.
I just want to jump in. Ronald Whitley, can you mute his phone? I don't have control, and we're hearing some feedback from your line. Thank you.
All right, hello, everyone.
That was
I'm sorry.
That's okay. That was a brief overview of our evaluation of the system. In essence, the system overall seemed to work very well. As I mentioned, we put the system in, and the blowdown basically shut off. We were taking blowdown flow measurements, 15-minute data for a period of several months at the site. Blowdown very rarely came on at that point. As you can see, they didn't necessarily need to blow down all of that material because it was coming out in the system. Again, the system was easier to clean, but I'll let the site folks address some of the more on-site issues. And I guess with that, I'll turn it over to Todd.
All right, thank you, Greg. Hi, I am Todd Kronlein. I am a mechanical engineer with the GSA Energy Branch in Region 4 in Atlanta. And I was involved with this project from a standpoint of finding a location to site this particular technology, and I wrote the scope to have it installed, as well as install some instrumentation that Greg needed on the project. And then I've also been involved, since the demonstration period has ended, I've also been in contact with the building manager and the O&M staff on site regarding getting the maintenance contract in place and addressing some maintenance issues and lessons learned that we've had in the about a year and a half since we've been living with the project, or living with the technology. Next slide, please. So that's a picture of the unit again, and the installation was relatively simple and straightforward. You basically have 3 items you need to connect to the unit, water, side stream piping off of the cooling tower, power for the unit, which is very minimal, and then compressed air. The UET unit itself only requires 120 volt service at about 16 amps, so it's very minimal. Now, the red pump that you see in the foreground, that is a something that is not part of the UET package. We specified that separately based on the flow, the desired flow that particular unit wanted. Our pump ended up being 280 GPM and about 10 feet of head with about a 1.5 horsepower motor. You may also see in that photo there's like a red rubber hose kind of draped over the pump and then zip tied to some of the piping. When I initially scoped out the unit, the vendor was using electric valves. There's 3 valves on the unit, and they were electric actuated. They then switched to compressed air, and so the project got awarded before we knew about the compressed air requirement, and so they installed that on site with the contractor. We found out that that particular hose that they used was more of a shop hose or shop quality hose that really wouldn't be good long term in the outside and having UV rays on it. So we ended up swapping that out with something sturdier. Long term, we're probably going to have a small project to hard pipe that compressed air in for something that is more appropriate for a long-term installation. Now you can see that we've got this unit located outside. We did this primarily because we simply didn't have substantial mechanic room space inside. We have 2 chillers that are in the building, adjacent to the cooling towers, and there just wasn't really any room to consider having it inside. The unit itself seems to be holding up, pretty well outdoors, with no cover on it. And part of me wants to say I'd like to see this. I mean, if I was doing this in another facility, I'd like to see it inside, but you do have the issue of it gets kind of messy to do the cleaning because of the water, and the material accumulation can be a little bit messy. So there's a little bit of a balance there. Outside, there's certainly a lot of room to work around in this particular location, and so far it seems to be working outside without any really accelerated say corrosion to it. And understand that Savannah, Georgia is located near the coast. You've got salt air, and it still seems to be holding up well. The unit has an Advantage Megatron XS controller on it, and it reads pH, conductivity of the basin water and the blowdown water and such. And that particular controller has the ability to connect to the internet or a BAS. However, for any of you that are familiar with the GSA security requirements, any IP addressable device has to go through our IT security remediation process. And so we don't have the controller hooked up to our BAS. It's something that we would like to see happen. We have to work with the manufacturer to get them to commit to going through the IT security process and possibly making changes to their unit for security purposes. But we would like to have that information more easily pulled into the BAS so that we can then share it back with the vendor. We have had some issues with the operation of the unit because our water quality down there changes. You get a lot of the water from the Savannah River is used in that area primarily. Very little of it comes from wells, and so you have seasonal changes with the water quality, and it's good to be able to respond to some of those changes in, say, TDS or silica that right now we can't respond that quickly to because we don't have easy access to the information. You literally have to go to the unit and manually scroll through the history of the measurements to see how it's operating. Next slide, please. Now, I was able to, last fall, I got a spreadsheet of the makeup water data taken from our meters on that unit, and I kind of did my own calculation, Greg, about what we had seen in the, I had 17 months of data after that unit was installed. The unit was installed and operational in July of 2016, and as of, I think, last November, the 17 months, the makeup water had accounted to about 2.4 million gallons. And then in the 17 months immediately prior to when we had that unit operational, it had, the makeup water amounted to a little over 3.4 million gallons. So in the 17 months since it's been installed, even with some of the maintenance issues I'm going to talk about, we've had a water consumption reduction of 29%. Now, some of the maintenance issues we had really arose from our slowness in getting the O&M contract modified to perform maintenance on the unit. And we did have a 9-month period where the unit was not cleaned at all. And what happened was we had some slime buildup and a little bit of scale buildup on one of the oil coolers for the, or oil pumps for the chiller. Once we got the O&M contract in place and we're performing the regular cleanings, even without any changes to the settings, the unit was working just fine again, and we weren't having any buildup anywhere in the system, and the cooling towers were still looking pretty clean. When my opinion was solicited after the the test demonstration was over, I actually said this quote here: "Don't be afraid of chemical-free systems." I've been in the engineering business for about 25 years now, and I worked in the private sector for about 20 years, and I can remember when we looked at chemical-free systems and alternative treatment systems many years ago, and oftentimes they didn't necessarily deliver on the advertised benefits. This one does. Even when we haven't, say, treated it the best and given it really prompt maintenance, it has still, for the most part, done its job, and whenever we have stayed up on the maintenance of it, it has performed well, and it handles all 3 areas of what you want a water treatment system to do with regard to corrosion, scale formation, or addressing scale formation, and then having biocides. Next slide, please. The actual cleaning of the unit is not that difficult at all. The tan bar or rod that you see kind of halfway down the right side of the unit in the picture there, that actually sits on top of the probes, on top of the reactor tubes, which are those green, Greg used the term canisters before. And so they power the tube and the insert, which are cathode and anode parts, if you will. Okay, the rods, if you're looking in the foreground of the insert, that small diameter rod that you see there is the anode. And so in order to do the cleaning, you take off that power bar, if you will, and then there's a lid, there's a plate on the top and the bottom, which allows you to pull that insert out to access the inside of the tube and access the insert where you can remove the mineral buildup. The mineral buildup has the consistency of wet sand for the most part. Now, your mineral buildup might be different because it is dependent on the composition of your incoming water quality, but for us, it was very easy to clean. Here the vendor tech was actually starting to scrape it off with just like a pocket knife. We went to a putty knife to make it a little bit faster. Super easy to clean. Then as far as cleaning the inside of the tubes, they provided a highly specialized tool, this metal rod that's wrapped in blue plastic there in the foreground of the picture with like a little spade end on it that's curved, so it kind of matches up with the reactor tube diameter, and you just scrape the walls of the tube and push out the material on the bottom. We're not showing the photo here, but this was our first time cleaning the unit, and we weren't super organized with with regard to our buckets. And so when we initially pushed out the material out of the reactor tube, we had a pile of like wet sand, if you will, right below the unit that we had to scoop up. So that's where maybe with say better processes in place, maybe some plastic and whatnot, you can keep the mess to a minimum, and therefore even if you have the unit inside, you wouldn't necessarily have to make a mess that would get in the way of other equipment in the mechanical room. Once we had our O&M contract in place and we had the initial service done by our on-site people, we also awarded a contract to the vendor so that they could come out on a regular basis, do the cleaning, and also check the settings. We had a cleaning by them a month ago, and they adjusted some of the settings based on their recent test of our incoming water. The silica in our water was higher than they saw the last time they were out at about 22 parts per million, and so they turned down the TDS reading down to 1,500 microsiemens. Now, our incoming water here has a TDS of about 400 to 500 microsiemens, and when we were running the chemical system, we were running it about like 2.5 times, okay, maybe around 1,200 or so. And during the demonstration period, the initial setting was 1,600, and a couple months later, they moved it up to about 2,400. And I think at the end of the demonstration, they actually went a little higher. They were close to 3,000, maybe 2,800 microsiemens, you know, off of like a 400 or 500 base. So we were running with about 5 cycles of concentration there. They've since turned it down because we had, you know, some time periods where, you know, like a 9-month period and another 7-month period where we didn't get the cleanings done, and we weren't, say, responding to, say, any major changes in the incoming water quality. So they turned it down somewhat to be a little bit more conservative, to, you know, kind of fully get the water in the proper state. You know, this particular unit, it doesn't address corrosion by, you know, instead of having chemicals in place. It conditions the water such that the water is not corrosive. And it does take a little bit of time for the unit to, you know, to get all of the water in that loop to, you know, that ideal state. And so they don't like to run the TDS very high until, you know, the unit is running and all of this water is nicely conditioned. And then once that's in place, then they, you know, will turn it up. I mean, at our recommendation, if you will, they will turn it up so that we can see more water savings while maintaining, you know, the proper water chemistry to, you know, handle corrosion and scale formation and still have the biocides addressed. Next slide, please. Yeah, so in our case, you know, we're finding that quarterly maintenance is really the right thing to do. You know, initially when we didn't know, neither the vendor nor us knew how frequently we would have to clean. You know, we were kind of making a guesstimate based on how much hardness minerals we had in our makeup water. The initial feeling was that, or this is the initial recommendation from the vendor was that we might have to clean it the first time at 3 months. And then once the system was in place and there wasn't a whole lot of makeup being brought in because we're running at, you know, a higher COC, they felt that our cleanings might be able to go every 4 or 5 months. And that still might be achievable with, say, you know, consistent regular cleanings and better, you know, control of the system. But right now, I think that, at least for us, a quarterly maintenance schedule is really probably ideal, and it's safe. In that particular photo, you can see one of the insert rods before we started to clean it. And you can see that the buildup on that center plate, you know, kind of looks like it's approaching the anode rod, which is set off to the side of that center plate. When the material in the reactor tube gets to be about 1 inch thick and maybe 1.5 inches thick on the inner plate, which is part of that insert, and then therefore it maybe begins to start to touch that anode rod, you begin to lose efficiency and effectiveness with the splitting of the ions that create the chlorine atoms, okay? So you know, you kind of want to find that right time period of when you do maintenance in the cleanings so that you aren't running with really caked up tubes and inserts for long periods of time. I'm talking about, you know, like months, where you would then begin to lose the effectiveness and efficiency of creating those biocides and separating out those particles. Now in our case, now that we have the maintenance contract in place, you know, there is a chemical company that is doing our closed loops. They're taking water measurements of the, you know, the closed loop, chilled water loop. They're also taking, you know, water samples of the open cooling tower loop. The maintenance of this unit is not done, however, through the O&M subcontractor that is doing our water chemistry. Okay, we have a separate contract with the vendor to, you know, come out quarterly now and inspect this unit and tweak the settings and also do the cleanings on it. All right, next slide, please. Actually, you know what? Can you go back for one moment, please? The vendor is located out of Phoenix, and so for us, our cost, the maintenance cost, it was a little over $6,000, I believe, for a one-year maintenance contract with 4 visits. And I know that the incoming water quality is different in different parts of the nation, and where this vendor is located out in Phoenix, they often see very high incoming hardness, over 1,000. And even with that, they have been able to run, this is what I'm told, they've been able to run TDS readings, up at around, COC readings of 10 to 15 with incoming water in the range of 1,000 to 1,500 microsiemens or TDS hardness, okay? So I think that there's certainly more that we could do with this unit in terms of getting water savings, but because of some of our own, say, difficulties getting our unit regularly maintained, we've kind of gone in fits and starts, and we haven't really been able to capitalize on what this unit can do. Even with the issues that we've had that we more or less brought on ourselves, we've never gone back to the chemical system since we had this installed and operational back in summer of 2016. Okay? All right, next slide, please. All right, well, that's the end of my portion. I appreciate your time, and I'll turn it over to Jesse Dean.
Yeah, hey, good morning, everyone. Thanks for taking the time to join us today. I'm a senior research engineer here at NREL, and I'll talk through the demos that we did at the Denver Federal Center. Okay, next slide. Before we get going on these, I think one thing I wanted to note about the 3 technologies that I'll be discussing today. So these 3 products were kind of grandfathered into the GSA Proving Ground, and NREL did not kind of go through the normal third-party M&V process that we would typically do, that you saw, for example, on the DWT project that was just presented. I think that being said, these systems all had very extensive automated metering infrastructure in place. So the Denver Federal Center, for example, has automated 15-minute meters on cooling tower blowdown, cooling tower makeup, on some of the chilled water plants, and then also had extensive building automation system trend logs. And so we essentially were using the existing M&V infrastructure that was in place for these. So a little bit different approach, but you'll see they all performed very well, and the results are pretty crystal clear on what we were seeing here. I also have 3 different technologies to get through today, so I'm going to be going pretty quick through these just to be cognizant of everyone's time. So the first one that I'm going to talk about today is a technology that's manufactured by Water Conservation Technology International. This was deployed at Building 25 at the Denver Federal Center. Building 25 is about a 360,000 square foot mixed use facility that consists of a mixture of laboratories and office space. I think that's important to point out because, I know there's some reluctance to install these on kind of high-tech buildings like labs and data centers, anywhere where you essentially have kind of mission-critical operations in the building. But you'll see that this product was successfully installed here. They have 3 500-ton cooling towers, and then they also have a plate and frame waterside heat exchanger for waterside economizer. Okay, next slide. So just a kind of high-level explanation of how this system works. Over on the right-hand side, you're going to see kind of 2 green boxes, and those are essentially alternating regeneration and brine tanks. So again, this is a chemical-free water treatment system. Those 2 tanks are essentially treating the incoming water into the cooling tower. You can get a detailed explanation of kind of how those are working within the report.
On the left-hand side, it's giving an explanation of, how scale, corrosion, and biological growth are controlled with this system. Essentially what we saw in the results for this system is close to 100% elimination of blowdown. The softening system that you see on the right, it does go through a regeneration process, and so depending on how much water is being ran through the system, so in Colorado, for example, depending on if it's the middle of the summer or kind of the swing seasons, that regeneration process changes a little bit. In the middle of the summer, 2 to 3 times per week, about 70 gallons of water is discharged, down the blowdown, and then in the fall and spring, it's about once per week. So, but again, there's no chemicals used in this system, and the softening system is taking care of everything. Okay, next slide. So the results that we saw here, I would say are similar to DWT's. There was a 23% reduction in the cooling tower makeup water, 99% reduction in blowdown. Of the 3 products that I'm going to cover today, this one had the highest cycles of concentration, essentially ranging anywhere from 30 to 75. But again, as Greg pointed out, once you get to above 30, it doesn't really have any benefit. You've essentially eliminated almost 100% of the blowdown. In terms of improved chiller operations, they did note a increase in runtime for the plate and frame heat exchanger and the water side free cooling, and observational improvements in water quality. I would say for this building and then the next one that I'm going to talk about, there was some existing scaling that was in the systems that was eliminated through the use of these products. I think to that question on energy savings, our experience is essentially, if there isn't any existing scaling that's in the, plate and frame heat exchangers for water side free cooling or in the condenser tubes in the chillers, you probably have a decent opportunity for energy savings. If those are pretty clean as they are, then obviously there's not an opportunity for energy savings. Again, on this one, since we did not have the M&V equipment installed beforehand, we didn't measure the energy savings here, but the site did report, an increased runtime of tower free cooling and energy savings with this one as well. Okay, next slide. Yeah, so this one also had a reduction in O&M. There was a 47% reduction in the total O&M hours for the product. The savings was $3,677 per year. And then similar to the DWT demonstration, there was also the elimination of the chemical costs. I think actually this system maybe still did use a small amount of biocide, and Tyler and Doug can correct me if I was wrong on that one, but there was a very significant reduction in the chemical treatment, and you see that in the cost that's listed there. Okay, next slide. So just quickly through the economics on this one, you're seeing a water savings of about $2,800 per year. Again, Denver does have cheaper water than the regional average for GSA. I think the regional average is right around $16 per 1,000 gallons. So, in these systems, things like water savings, chiller energy savings, and maintenance savings all do have a big impact. And so, you can see, for example, just the reduction in the chemical costs was about the same as the cost for the water savings. But the total maintenance savings was $6,445 per year, and the simple payback on this one was 3.2 years. Okay, next slide. So the second one that I'm going to go through today is what I would characterize as a more traditional water treatment system. This is manufactured by a company called Terralin. So unlike the other 3 technologies that we're going to discuss today, this one does use chemicals. You can see the 3 different vats of chemicals that are used in the picture on the left-hand side, and we'll go into the differences in the types of chemicals that they're using on the next slide. So this particular solution, or system, was installed at Building 67 at the Denver Federal Center. This is about a 340,000 square foot office building. Again, they had two 600-ton cooling towers, and then they also had the water side economizer. Okay, next slide. Yeah, so in a normal cooling tower water treatment system, the three primary chemicals that are used for water treatment is a scale inhibitor, a corrosion inhibitor, and then a biocide. And normally kind of the rate limiting factor for the cycles of concentration that the system is going to be operating at is the effectiveness of the scale inhibitor. So for this particular system, they're using the same corrosion inhibitor and the same biocide, and are using a much stronger scale inhibitor. And so in this particular case, it's still a chemical-based water treatment system with a stronger scale inhibitor. It does have a new kind of manufacturer-specific kind of control and automation system. They claim to be able to operate up to a COC of 50. We did not see that in this demonstration, but you will see that there was still very significant water savings. The site also installed a side stream filtration system with a glass media filter. And that glass media filter was flushed pretty regularly with about 300 gallons of water being flushed when that was going down the drain. But again, kind of flushing that glass media filter was the primary use of blowdown water post-installation for this case. Okay, next slide. So the total savings were similar here. A 94% reduction in blowdown versus a 99 in the last one, with the cycles of concentration that ranged from 13 to 18. It was my understanding on this one that this had the most scaling of any of the other systems, and so they did have very significant changes in their plate and frame heat exchanger operation. Unfortunately, we did not have BAS trend logs that were set up pre-installation of the technology to correlate the ton hours of cooling with the kilowatt hours of chiller plant usage. So we do not have chiller savings on this one, but it is estimated to have the most significant energy savings of any of the technologies that we looked at here. Okay, next slide. Yeah, so on this one, given that there was chemicals being used, in this case it's kind of the opposite of the other two products, where the chemicals actually are more expensive than the baseline chemical usage. And so you see, for example, there's an increase in the annual O&M contract that's associated with the chemicals being more expensive. That being said, given that this results in a cleaner system, there was a significant reduction in the maintenance labor hours. And so you see a 48% reduction in labor hours, but a slight increase in the chemical costs on this one. Okay, next slide. This particular product had a 8-year payback, so the payback was a little bit longer than the other one. Again, and that's primarily driven by those chemicals being more expensive than the baseline. You do see those significant water savings. They were able to eliminate most all of the blowdown, and again, as very favorable economics. The comment there on the local rebates, the Denver Federal Center is a large campus here in Denver, and they have a single kind of point of entry water meter that is used for billing purposes. And although there are local rebates for cooling towers, I think the numbers was something like only one cooling tower per site is eligible for that rebate, or like one system per meter. And so again, the economics could have been significantly improved in other cases, for example, where GSA owns and operates a lot of buildings that do have kind of a single, incoming water meter and can capture those local rebates. So I think another thing to just keep in mind is if you're, installing these, make sure to also kind of check with your local water provider and see if there are rebates available. Okay, next slide. So these systems at the Denver Federal Center have been operational for a number of years. You can see the date installed over there. So since deploying these first two, they also deployed them at a number of other facilities in the Denver Federal Center. And you can see that the total annual water savings for all of these systems combined is on the order of, over 6 million gallons of water per year. I think one thing important to note, and has been on my mind lately, is, GSA has been doing a lot of energy savings performance contracts over the last few years. In those, you see a lot of fixture retrofits and kind of water savings measures inside of the building. And so I think for a lot of the GSA sites that have already gone through an ESPC and kind of upgraded fixtures and reduced water from that perspective, this is a great kind of complementary technology to further reduce your water savings and help meet your water savings targets. And as you can see, there's, very, very significant water savings that are achievable for each of these systems here. Okay, next slide. So the last one that I'm going to talk about today is a product manufactured by Silver Bullet. It's an advanced oxidation process technology. This technology actually won an award through the Industry Growth Forum at NREL in 2012 for a product of the year and received some kind of entrepreneurship and technology development support. And then after that was installed at Building 95 in the Federal Center. Building 95 is also a mixed-use facility with a little bit of lab and office space, and they have two 250-ton cooling towers. This technology, I would say, is different in the others in that it can be installed, really quickly, and it doesn't impact any of the existing systems. So you can leave, all of the existing chemical water treatment systems in place and unchanged. This box that you see here with these two blue tubes essentially gets mounted to the wall. And then on the next slide, we'll kind of walk through how this technology works. Okay, next slide. So the technology essentially kind of pulls ambient air from the room, and it's pulling those through a series of ultraviolet lamps and other components that kind of negatively charge the oxygen atoms in the air. And then the interaction with the cooling tower is essentially an air hose that's routed from the bottom of the unit to the basin of the cooling tower. And it has a diffuser in it that kind of diffuses this oxidized air into the basin of the cooling tower. And so that air oxidizes minerals, it oxidizes the contaminants in the water, it kills the bacteria, and it also helps to break down some of the calcium buildup related to some of the scaling. So again, an interesting technology, I would say, is probably one of the lower risk ones to install, given that you can operate the system as normal and then kind of go through that process that Todd described of adjusting, some of your cycles of concentration set points. You can go through and adjust the amount of chemicals that are using and do that in a way that's kind of systematically deployed to make sure that this is operating, how you want it to. Okay, next slide. The savings we saw on this one was 26% water savings. We did not see as significant as improvement in COC. I think the average on this one was about 11. That being said, even though they operated at a lower cycles of concentration versus the other technologies, it did still save significant amount of water. They were also able to completely eliminate all the scaling and corrosion inhibitors that they were using. They were still using a little bit of biocide on this one, but we conducted some follow-up water sampling from the basins of the cooling towers, and this one actually had the lowest levels of biological growth of any of the systems that were tested at the Denver Federal Center, and so it looks like they could have, fully eliminated all of the chemicals that were being used on this one. Okay, next slide. Again, similar to the other ones, there was about a 50% reduction in the operation and maintenance. The slides indicate that there was a significant decrease in condenser tube fouling. I would say the system was honestly pretty clean prior to being installed. There was some tiny specks of scaling in the bore scope, but they were very small. But there was a noticeable improvement in the scaling and the condenser tube fouling. Okay, next slide. So I think my final slide here is just on the economics of this system. It had a $3,000 per year water savings, maintenance savings of $2,500 per year, and a simple payback of 2 years. And the systems themselves were purchased, but there's also an option of kind of leasing the equipment from this manufacturer. And I think Doug and Tyler can kind of get into the benefits of that one. But I think the summary for the Denver Federal Center is, they have installed a number of different systems across a lot of buildings that have been operating for a number of years, including kind of high-tech, mission-critical facilities, and seeing that they have been very successful, and kind of goes to Todd's point that, these technologies do work well. Okay, so that's all I have. I think next one is I'm going to hand it over to Tyler Cooper and Doug Bachman.
Look at that. Thanks, Jesse. So, yeah, I'm Tyler Cooper. I'm a mechanical engineer here in Region 8. I have Doug Bogman with me. So we're both in our facilities management group here in Region 8. We'll go next slide. So, as Jesse alluded to, we've done quite a number of cooling tower water treatment installations here, both at the Denver Federal Center and at other sites across our region. At least here in Denver and most of our sites, we have a pretty standard 5-month cooling season, and it's generally pretty much the minimum standard we look for as far as seeing a positive ROI with one of these technologies. Knowing your daily hours of tower operation is going to give you a lot better idea as far as how much potential you have there as well. Obviously, the more we see these towers running, the more potential savings we're going to have available from those. So as it mentions, you can have a 500-ton tower that's running 24/7. You're going to get more savings from one that's running running your typical 10 hours a day. So the other pieces I think we look at as far as that is we typically have harder water here, not as good water quality, so that's also going to lower our savings potential, whereas you see somewhere with softer water that you're not having to treat that, you're going to have more capability there as well. So next slide. So one of the things that, given what Jesse said, we had installed a lot of these technologies prior to the putting them in testing with the GPG program. But one of the things that we found both for our internal M&D purposes as well as for GPG purposes is you can't measure what you don't meter, obviously. So what we've found is, at least at a minimum, we want to see water meters on your makeup water for the tower. And then for most of these installations, since we are mostly eliminating flow down, the flow down meter is not necessarily as critical, but it is good as a safety double check there to make sure you're not wasting water. The other piece that we had was the electric meters covering our chillers or our chiller plants. Given how a lot of these towers operate, or these systems operate, you are going to see energy savings across the board, both from the with your higher heat transfer rates with the chillers or flat plates that are tied to the system. And then within that, most of our buildings do have advanced metering systems available, so that just, if tying it into advanced metering makes it easier to access that data and then get that real-time ongoing performance available. The final piece that we did with these installations was we made it a best practice for our region is installing these side stream filtration systems. We've done most of those with the glass media filter, and that's just to keep making sure we're maintaining that high quality going into these systems. So, next slide. So one of the biggest challenges we've had here in the region probably is just successfully integrating these programs with our O&Ms. Old habits are hard to break. So what we found is O&M project managers, they're tied to existing ways. They're used to the technologies they've been using, the existing chemicals that they know work for these towers. So they're always hesitant to try new technologies within that. So one of the things that has made these more successful is closely working with the O&Ms making sure they understand exactly how the system works, what the system's supposed to be doing, what those specific water quality operating parameters are for. So a lot of times these will, with increasing that cycles of concentrations, you are going to see higher levels of certain system parameters that you wouldn't typically see. Within that, obviously working within modifying the O&M contract, most of these technologies we're seeing a large decrease in the amount of maintenance hours required from the O&M, less tower cleaning. Ideally, you're going to with some of the scale reduction on these, you're also seeing a lower frequency that you're having to punch the tubes on your chillers and clean out the scale there as well. So within that, just building up your overall trust for the system with the O&Ms and making sure that they understand that. The other thing is it's helpful to have an online, so if you do have an online reporting system available, you get real-time updates for the system and just being able to monitor and track what's happening with that. So next slide. So within that, some of our lessons we've learned, inspecting the water circulation in the tower basin. The water should be able to easily flow under the media. I know a lot of what we've seen in a few cases is we'll have adequate water quality in the tower with testing, but you'll still have algae blooms taking place if you're not getting proper water circulation throughout the tower. Once again, going back to the reporting of it, you want to be able to pull historical data from that controller that's operating the system, be able to export that for future MV purposes and just quality control purposes as well. So as Jesse mentioned, one of the things we've looked at with this is Silver Bolt particularly, but applies as well, is looking at leasing some of these technologies. It's a lot easier to integrate into your O&M contract at that point, and then by leasing the technology, you're also you can include some of those ongoing maintenance costs in keeping that technology running and operating at its full potential. Within that, one of the things we recommend is performing a borescope inspection before the install. This goes back to measuring the scale in your chillers. With most of these installations, with these technologies, we've seen a large reduction in an overall scale buildup. And that's where, with these ones, we didn't have the electric meters on the chillers installed beforehand to measure that savings. We have we've been able to get a lot better performance from our chillers as a result of that scale reduction. So performing that borescope inspection allows you to make that valid conclusion and actually get measurements on what's happening there. The last piece is making sure you're maintaining the service reports. So for all of these, we get monthly service reports as far as the water quality, how that's performing, what we're getting for active cycles of concentration, what we're seeing with the water quality for that time of year, and what any other maintenance issues that might have arose with those towers, and what we need to address moving forward. And with that, that's all I have. So.
All right, great. Thank you, Tyler. So this is Jay Fine again. I'm going to take you through the rest of the presentation today. I'm going to talk about alternative water technology takeaways. Can you go to the next slide, please? All right, great. So this slide is a roll-up of the four technologies that you heard about, and it talks about the water maintenance savings for each of those. So the way this table is set up across the left-hand side, you'll see a couple of different attributes and measurements that were taken. And then going across each of the columns, you'll see each of the four technologies that were presented today. So I don't want to go through every number on this, but I thought you can look at this and you can see which of these measurements or attributes are important to you. You can look at those, but I do want to point out just a couple of quick things. If you look at rows, I would call them 2 through 4, where it talks about the cycles of concentration and the water savings, you'll see that each of the four technologies, as was already mentioned, each provided increased number of cycles of concentration, which resulted in pretty significant water savings that range from anywhere from about 23%, I think, all the way up to almost 32%. So all of these did perform very well. And then if you draw your attention down to the bottom of the chart where it says annual maintenance contract, I do want to also point out that here, 2 of the technologies actually increased our maintenance cost. So, you need to look at every one of these and which are the important aspects of the technology that are of interest to you. However, I also point out on the next slide, if you'd switch, please. So this takes into account all the economics for these. And the biggest takeaway from this, I think, are the 2 bottom lines. And those are, when you look at the simple payback, those are all of them are between 2 and 3 year payback. And the SIRs are also pretty significant, a great SIR in all of these. Now, one of the things that is about this chart, you'll notice that, you heard different payback periods, you heard different information in some of the presentations. And that's because in the presentations, they use the actual water costs in those locations. On this one, we try to normalize the data by using what our annual water cost is for all of GSA, across all of GSA, which is $16.76 per kilogallon. Okay, next slide, please. And these are just a couple of comments about alternative water treatments and some recommendation items, some deployment items for you. So one of them is that you can put these on, you can retrofit any cooling tower. These can be added to those systems. The second thing is that, we call it straightforward, but essentially what we're saying is these are add-on systems. You don't have to replace any of your existing equipment that you have. They're all add-ons that can be included and added onto any system that you have. And the last item on here is that these 4 were all successful, but we also have 2 additional alternative water technologies that we're currently testing right now. Okay, so with that, this takes us into our Q&A. We do have a number of questions. So for those of you that were presenters, what I'd like to do here is I'm going to go through and read the questions, and then I'm going to call on a couple of you individually to answer. If we need to bring in a couple of you to answer them, we'll do that as well. So the first one is for you, Greg Tomberlin. It's a couple of questions about the water quality in Savannah on the electrochemical water treatment. So it talks about what's the incoming water TH, and then also does the demonstration site have hard water? So can you just talk a little bit about the water quality there?
Yeah, I don't know if Todd is still on. He might have a better handle on exactly what that quality is. I could probably pull it up. But Todd, do you know offhand the quality there at Savannah?
I don't think the quality was considered to be hard. Okay, the water quality was actually pretty good without a lot of hardness minerals in it. I did have a sample, some data from the makeup water, but I don't have it with me at the time, so I don't know the exact numbers. But just in general, the feeling was that the water quality was on the softer end of the scale for typical utility water supply.
Yeah, I was trying to pull up some information. I just see some total hardness of the makeup water was 90 ppm in one data sheet. I think that's probably fairly consistent.
Okay. Todd, I think this next one would be good for you. It's what are the safety concerns when cleaning it?
We had no safety concerns. The mineral buildup is not toxic, and it's basically the equivalent of scale that would form in a system if we didn't have the scale, chemicals, say in a typical system inhibiting scale formation. And we were told and we believe that that material buildup that we clean out of the system can be disposed of in the trash. Again, it was non-toxic and generally consists of hardness minerals.
Okay, great. Thanks, Todd. All right, Greg, I'm going to go back to you on this one. I have centrifugal separators for my towers. How does this system compare to the electrochemical system?
I'm not sure of the question. The centrifugal separation system is a completely different system than what we're talking about here, but like I said, I'm not sure I understand that.
Okay.
Also, are the centrifugal separators more for collecting solids, I think? So, you know, if it's a solid separator, it could actually, I'm going to say, enhance to some degree the operation of this DWT unit. One of the things that we found is that when the unit is operating right and it's killing biocides because it's generating chlorine ions, you will have some of the biologicals accumulating in your cooling tower basin, and so possibly that centrifugal separator that he's talking about might actually clean that up for you automatically, thereby maybe reducing manual cleanings of the tower.
Okay, great. That's helpful. All right, so we're still on the electrochemical water treatment system. So this question is about why did they use compressed air actuators versus the electrical, and what's the additional cost of maintenance going with air versus electric? I believe the answer to this is that that's a manufacturer change. It wasn't an individual location change, that all the units are now going to air. Greg or Todd, do you have any additional insight into that?
Yes, I actually asked that question too, because of the surprise in having to provide another utility. They said that the compressed air valves, they actually have 3 valves on the unit that receive compressed air. They've got a treated water valve, a vent valve, and a drain valve. And the actuation with the compressed air was faster than the electric-driven ones, and so that's why they made the switch to compressed air. And actually, let me also say this too. I think prior to this unit, their standard was compressed air, but they had been looking into going with electric so that the unit was more packaged, in essence, bring electricity to it and that's all you need, type of thing. Everything is electric driven. And while they were considering it and doing some, work on making that happen, they didn't go with it at this time, and they're probably still not going to, use electric because of the performance characteristics of the compressed air driven valves. And we did not find any, and I'll add to that too because of the maintenance side of the question. We haven't seen any increase resulting from the compressed air valves versus what we might encounter with electric-driven valves.
Okay, great. And then still on that same system, the question is about if we measured for Legionella. Greg, do you want to take that one?
We did do, it's been a while, we did do Legionella testing there, and we didn't see any problems with that. I think we generated biocide quantities that were, made the system comparable to when we were using chemicals. I think after the fact, Todd said at some point we might have lost some biocide production when, the maintenance wasn't kept up, and I don't know if you could speak to that, Todd, but we didn't have any problems during the testing period.
No, you're right, Greg. We didn't see any issues with that. What I'm thinking. One of the things that I do want to bring up regarding the unit and chlorine and the biocides. The unit itself doesn't. There's an anode cathode process that is occurring in the reactor tube, okay? And it activates chlorides already in the water to make the chlorine biocide, all right? And that's actually an important thing to note because if you, let's say your facility is on a well water system and you don't have any municipal-like water treatment, which, generally they all use chlorine, okay, in order to disinfect the water. So if you don't have any residual chlorine in your water supply at all, you're going to have to supplement their system, and what they recommend is supplementing it with a water softener, because a water softener brings, salt water, sodium chloride, into the system, and so that you then have that NaCl in there, which the process can strip out that chloride atom and activate it to become your biocide. Now, when we did our water quality test ahead of having this installed, there was enough residual chlorine to make our system work. I do not remember what their level is. It's something small, maybe around 5 parts per million. But there is a number that they have where if your residual chlorine on your incoming makeup water is below it, then they recommend having like a brine system added so the system can activate the chlorine to make that biocide.
Okay, thanks, Todd, for adding that in. That's good. All right, I'm switching systems now. So Jesse, I think this one would be for you. This is about the salt-based ion exchange. The question was that they didn't see salt O&M costs on the slide for regeneration. Was that in the maintenance cost savings?
I'm not sure. I'm going to kick that one over to Doug real quick. Before I do that, though, I would say on the Legionellas question, there was follow-up water sampling conducted at all the Denver Federal Center sites, and they also didn't see any Legionellas buildup in any of those.
Thanks, Jesse. All right, Doug, do you have any insight into the maintenance costs for the salt? Or Tyler?
It was like $700 a year is what I have. I can look at my spreadsheet and get back to you with raw numbers. But
Doug, I think the question is, Doug, the question is if it was included in the maintenance cost savings that were shown on the slide. Was that cost included in the?
Yes, it was.
Okay, great, thank you. Okay, and then moving on, there's a question about have these cooling water conditioning systems been tested in regions with softer incoming water? So I think the answer to that, I'll take the first shot at this, which is that these are all of the technologies that have been tested by the GSA evaluation program. There could have been other ones maybe that were installed in other GSA facilities but were not part of an evaluation, and there also could be others that maybe NREL tested in other locations. I guess I'd open that up to either Jesse or Greg if you've done any other evaluations of these technologies in places where that might have softer water. Either of you?
Yes. Nope. Yeah, we did do a demonstration in Las Vegas for the DWT product. But I don't have, specific results for locations with softer water. I think Doug and them maybe again can comment on that one. And
yeah, that might be good too. So yeah, Doug or Tyler, have you guys also installed or tested these in other locations that might have softer water?
I mean, we wouldn't consider Denver to have super hard water in the first place. I'd say it's more middle of the ground. But beyond that, we haven't done any other installations outside of the Colorado area. Colorado and Utah, which Utah does have much harder water than Denver. But
okay, thanks. All right, moving on to another question then. So this question is about if we monitor corrosion rates for any of the systems. I think Jesse and Greg would like maybe both of you could talk about your individual projects. Jesse, you want to go first?
Yeah, I have to say on the DWT system, we didn't monitor corrosion on that system.
yeah, and again, in our reports, we also were not monitoring that. I don't know if Tyler and Doug did monitor that separately or not.
Yes, we monitor corrosion and bacteria along with Legionella. We do the whole package.
And do you use coupons or you use corrosion meters, do you know?
It would be nice to have the meter, but no, it's coupons.
Okay.
And that tells us, the effect that water chemistry would then have on the system that, as it's going. So we do.
And
okay. All right, moving on to another question.
I was just going to say, Doug, were those results still positive, or can you kind of go over what you saw in those? On the corrosion control pumps?
Yeah, and all the results shown on, we had the iron and we had copper, and everything met the cooling tower industry standards, and it was all low. Nothing on any of the systems was corrosive. We saw the standard allowed measurement of each coupon. It didn't go beyond that. But we also were measuring. We measure our makeup water too, that's coming in from the city, and so we're able to see the difference between, because we could be adding worse water into our system than what we're measuring for. So when we do, that's why we want to look at our reports every month to make sure that what's causing the increase of maybe iron or copper or and that's been a pretty good lesson learned there, and I believe that the other system, when they were looking at it, that you can dump the water in and you got to remake it back up again, to get a higher COC. So.
All right, let me move on to, I believe this is our last question. Were there any issues with soft water causing leaking pipes? Maybe Doug or Tyler, maybe we start with you guys. Do you have any insight into that?
No, and we've got all iron and steel pipes in our system, so we haven't had any issues with that, any of our installations. So, I think the main problem we usually run in with the cooling towers is just leaking the float valves and everything, and then more performance with the towers, nothing with the actual pipes, though.
Well, the other thing, without getting too in the weeds on it, is that with the soft water, it needs to be maintained within its own chemistry, or it can be corrosive, And so that's where the science and the technology inlays, because everybody will freak out thinking, oh my gosh, the basin's going to go and whatnot. But if you're maintaining what the technology is supposed to be doing, it does not become corrosive to that.
Okay, great. And then Jesse or Greg, did you have anything to add to that?
Nope. I would say though that in the reports we do have kind of the GSA required water quality parameters, and then for each one of those we did take those monthly reports and compare those there. So yeah, even though we didn't get into kind of the water quality results in here, I just wanted to make sure people knew that those were done and are in the reports.
Okay, fantastic. Okay, so Andrea, can I turn it back to you to finish us up with the slide to talk about the survey?
Yes, thanks, Jay, and thanks to all the presenters. So as we mentioned, if you registered for the webinar shortly after, within a few minutes, you'll receive a survey. By completing the survey, you can request continuing education credit, and we appreciate your feedback one way or the other. And if you don't receive a copy of the survey, please reach out to Michael Hobson. And with that, thank you to all of you for being here and to the presenters, and we look forward to seeing you on the next webinar. The next public webinar will be in May, and we'll be sending out a webinar announcement. Thanks again, and see you next time.